In this video, we shall learn how to do influence diagnostics using R. First, quickly recall why we are interested in finding the influential points. Because remember, an influential point is like this, where I have a point here, one single point, and that causes the fit to change so much that it fits neither that point nor the bulk of the point. Obviously, if you have even one such point, it is going to completely ruin the fit. That is why we are interested in detecting which are the influential outliers. Now, when it is a two-dimensional setup like this, you can easily check that by making a plot, which always remains the best way of doing things. However, if you have a multidimensional setup, then finding one such weird point is very difficult. That is why we take automated ways of finding them. What should we do after we have detected an influential point? Well, that depends on why the influential point came in the first place. Roughly speaking, there are three ways by which an influential point may occur. Number one, it could be just a typo. In that case, of course, you need to be able to detect it and correct it. So you might think of this technique, influence diagnostics, as a way of spell checking a typo. You cannot use a spell checker to find a typo in numbers, so this is one way of doing that. The second type is where it is actually outside the population. Now, whenever you are carrying out any statistical analysis, you have in mind some kind of a population for which you want your inference to be valid, and all the sample points must be from inside that population. Now, occasionally something may enter your sample inadvertently which really does not belong to that population. For instance, you might be interested in studying the behavior of students in a certain economic class, say somewhat like the lower middle class in say West Bengal, and for that what you do is you go to various schools that are frequented by these students. Now, it may happen that some occasional students in such a school is actually not really fit in, so not really belonging in that school. So, for example, they are going to leave that school within a year. They are there only because they have missed some deadline in getting admitted to some better places, and they are there only to maintain continuity for a year. So, in which case, if you put such a student in your sample, your entire conclusion will become ruined. So, you need to understand that this particular student which has entered your sample is really not part of the population that you are interested in studying. In this case, what you should do is simply throw away this influential observation. Now, the third way by which we can get an influential observation is when you are having an extreme case inside your population. Like you are carrying out some clinical study and you have taken into account lots of different factors that are going to be of importance. But then you find that if certain weird combination occurs, for example, a woman is pregnant and she is also under a particular type of drug, then the effect of your treatment is drastically different. Now, you had no way of knowing that this strange combination, pregnancy together with that drug, is going to have an effect. So, you really did not keep pregnancy or usage of that drug as one of your factors. But if that is the case, in that case, your influential observation is very important. Then your final conclusion should be that if that weird condition does not occur, then follow this model. If that condition occurs, then do something else. So, in this case, you really do not throw away that point from your study, but you set that point aside, fit the model to the remaining bulk of the data, and then consider that point separately. So, depending on the reason behind the genesis of the influential point, you may need to do these three things. So, let us see how we can do influence diagnostics using R. for this purpose, I'll be using this data, which is called life cycle savings data. It's a data from economics. So let's take a quick look at what this is. And I do not think that I know enough of economics to really understand what this data set is all about. So if you want, you can take a quick look at the data and see what it is all about. So there are got various variables. SR, which is aggregate personal savings, and these are two different types of populations, 75, and DPI, real per capita disposable income, whatever that means, and DDPI is the growth rate of that. So briefly speaking, that there are a number of countries. So the countries are the basic units in our data set, and for each country we have a number of variables measured. Out of these, this SR is our response, and the remaining things are the predictors. So let's quickly take a look at all the countries that I have. So I will type row names, life cycle savings, and these are the countries that we have. We have got Australia, Austria, Belgium, Bolivia, etc. So all these countries. And these observations are all the average things over a 10-year period. And based on that, we want to check some model which they call is the life cycle savings hypothesis. And for that, they need to fit a linear model with SR as the response and the remaining 4 as the predictor. So let's quickly do that. And let's quickly do that. So we'll have these names. We have the names. Where are these? These are the names. SR POP 15, POP 75. I will carry out the fit. I will fit SR onto all the rest. This dot notation means all the rest. So, and I get a fit. I do a summary. These are my estimated things. These are the standard errors, and some of them are significant, some of them are not. Now, I'm not going to discuss whether this fit is really conforms to that model or not, because I really do not understand the model. I would just draw your attention to this multiple R square and adjusted R square. They are apparently notoriously low, but as our book, the Belsley-Koo and Wells book remarks, this adjusted R square is fine with them. That is, for this kind of study, so that is the typical value that you will attain. So they are not shocked by this value. They are still continuing their study even with adjusted R square, which is apparently as low as this. I had already commented earlier that there is no absolute threshold that you can give for R square or adjusted R square. It is very domain specific. So in this domain, they claim this is good enough. Okay, so now I want to get all those quantities, that is, which of these observations, now let's quickly see how many such observations are there, that is, how many such countries we are considering. We have 50 countries, so we need to know whether out of any of these 50 countries, something is weird. Now, how do I do that? We have learned about various things, DF-feed, DF-beta S, COV ratio, blah, blah, blah. Now, there is a nice function which is inside R, and that will kind of solve everything for you. And we will show that first. It is called influence measures. You just call influence measures on fit. You do not need to install any package or anything for that. And it will give you a list of all the things that you have described and also draw certain conclusions. So let's do that. And it gives you a huge list. Let's take a look at that. So for each value of I, that is in our case for each country, it will compute the following things. It will compute the df beta s quantity. So dfb, this is for the intercept, this is for pp15, that is one of the regressors, this is for another regressor, this is for this and this, so there are 4 regressors plus the intercept term. These are the df beta s values. Similarly, these are the df fit values. They call it df fit, but actually they are df fit s values. These are the curve ratios, and they also print some other things which did not fit in the table, so they have been delegated to the next line, next punch. So this is called cook.d, which is the abbreviation for Cook's distance. Now we have not talked about Cook's distance, so let's take a quick look of what that is. We have already talked about df fits, that is the influence of a point when we are trying to predict the y value of that same point itself. So for that we have deleted that case and then tried to predict the y value of that point based on the remaining n-1 points. Now one problem with this is that when we are working with n points, we might be interested in other things also. That is, you drop the third point, you want to know how that influences the prediction for the 10th point. In this case, we dropped the third point and we became interested in how the prediction of y value for the third point itself was affected. Now, if we want to take all these cross terms also, then there are too many of them. There are n square many of them, and it is difficult to summarize them. Now, Cook's distance is a way of doing that summarization, and it is defined in this way. Cook's distance di stands for, so here I is the particular case that you are deleting. Cook's distance for that is the following. You try to predict all the things using the entire data, that is your yj hat. Now you drop that ith case and again you try to predict all the things, that is your yj hat I. You take the L2 norm between them. So you take y hat, the entire y hat based on the entire data and also the entire y hat without using the ith case. But you are still predicting everything including the ith case. Take the L2 norm, that is the numerator, and standardize it by dividing it with p plus 1 into sigma square hat. Remember, when you are using sigma square hat, you are using the full estimator. That's how Cook's distance is defined. I am not entirely sure why you are not using sigma square hat I. Possibly this will give you certain better mathematical properties or something like that. I do not know. And this p plus 1 basically is the total number of columns in X. So p many regressors plus there is one intercept term. So if you do not have the intercept term, you drop the 1. And remember, this is not really for the ANOVA setup. This is for the multiple regression setup. All the things are continuous. Then the di's give you one particular vector, or you want it to up to dn, and that is what was printed. So naturally, if any of these quantities is large, then you suspect that that has a strong influence on the quality of the fit. Okay, so now that we know what is meant by Cook's distance, you can see that this is the list of these. Now, they also print the head values, namely the diagonal entries of the hat matrix. Now, based on all these things, somehow you have to draw a conclusion. So, which are the influential cases? Now, they have various cutoff values for that. And these cutoff values are based on some heuristic, some asymptotic Gaussian distribution, etc. I'm not going to go into all those cutoff values. Something is, you take the total number of regressors divided by that n. If it is exceeds 3 times that, then you consider that as significant, and this is a rule of thumb, etc., etc. If you want, you can take a look at Wellesley-Poo and Wells, and they give you all those cutoff values with some justifications. But here they will give you directly the conclusion. They have added one column called inf, that is whether it is influential or not. If they put a star, that means it is an influential point. So Chile, I think, is one influential case. Now, how they have decided, that depends on some composite things. So they have used DF beta A, they have used curve ratio, they have used this and that, and finally they say Chile is one thing that requires a second look. And then you have got United States is another one. Then you have got Zambia and you have got Libya. So these 4 cases requires a second look. Possibly these are influential observations. So you should make sure that they are not ruining your feed too much. They should really be in your data. There is no typo for them. So you should look at those things. Now this is kind of a blind approach. So they computed lots of numbers and finally somehow they gave you this thing. But most likely you will not be satisfied with that. You would want to take a look at the individual things. So for that what I have done is you can extract the various quantities. For example, you can extract the R student values. So the function R student will do that. So let's just do that extraction. And you might plot it with that AB line 0 and you can try to find out what the things are. So let's do the plotting. And when you see this plot, you naturally want to know what this point is. That looks like an outlier. So our student will really not tell you whether it is an influential point or not. It will tell you whether it is an outlier or not. This is an outlier. Here is yet another one. Now you will be interested in knowing exactly what country does this correspond to. There is a function in R which will enable you to do that. That is called identify. So it is very much like the function locator, which we have already talked about, except that it will also label. So you write identify, then the value that you have plotted, then you also provide a label. In this case, I provide as labels the row names of my data set, namely the names of the countries. So the moment I do that, I execute that, nothing apparently happens. You go to the plot and you will see that your cursor has changed to a plus sign, much like locator. It is calling locator internally, and then you take your cursor to that point and left click and you will see the name Zambia. So that is Zambia, which was indeed identified as one of the influential things. You saw that we had star against Zambia. Now let's look at this fellow, and this is Chile. Now observe that all the other 3 things that it also got us, what for us, 3 or I think, not 3, I think it discovered how many for us. Let's just see. It discovered 4 influential points for us. Out of them, only 2 are actually outliers. So the remaining things are really not outliers. So they are inside this. So merely by looking at the residual plot, you will not be able to understand that there are 2 others which are also potential problem points. So you can do this for all the things. Now what I will do is I will just convert this. I want to come out of this. It is tilde plus. So I will just do a right click and then I will come out of this identify loop. And now this is quite useful, so I will write a little function which is called checkpoint. I just call it checkpoint. What it does is it first makes a plot and then it also calls identify with that suitable label. So I will just load that function. So I've loaded the function and then I can just call checkpoint rs directly and it will do the job. Now let's take a look at the head values. Now it is commonly considered that if some head value is large, that requires a second look. So let's just take a look at that head values. So what I will do, I will again go there. Automatically identify has been called. So this fellow seems to be pretty off. Libya. And this fellow seems to be weird also. United States. This thing, let's take Japan. What is this? Ireland. Okay, so Ireland also not too bad, but something that is not like the bulk of the data. So maybe you should take a closer look at that. I right click and come out of it. Okay, now let's take a look at the effects. Same story. So in this case, I am just looking at each one of them individually so that you get a better idea. So these are my DF fits. So how they influence the fit. So this one is an influential observation so far as fit goes. Japan. This one, Zambia. So these were already reported when I looked at my influential values. Ireland was really not reported because it was not that influential. It was more or less close to the bulk of the data. So this is how you carry out this influence analysis. But above all, you should remember that all that it does is it just draws your attention to certain values which are potentially dangerous. Now you should take closer look whether there's typo, domain knowledge, etc., and then carry this on.